So let's talk about the derivative. And I think we've seen this name before. But here we'll talk about it a little bit more formally. So what the derivative is, I hope you've watched my initial explainer video talking about the definition and doing a calculation. We'll go through it again, but not in as much depth because I'm presuming that you've watched that. But to connect this back to what we've done before, you take a function like y equals x minus 2 squared, like for instance. I mean, I'll do this with a schematic picture, but you can keep this concrete example in mind. And we have talked about this idea of instantaneous rate of change versus average rate of change. And so if you take, say, some point x, and here's the point x, f of x on the graph, and then you go out by some amount, either to the right or to the left, but people often draw it to the right. You go out by some small amount, h. Think of this as a very small, like h is a variable, it's some number that's very close to 0. But just for the purposes of being able to see the picture, I'm going to draw it as if it's kind of large. And you have this point x plus h. Now f of x plus h. And you can look at the average rate of change from these 2 points, which is just going to be the slope of the line. It's going to be the slope of the secant line between those 2 points. Secant line, of course, being the line that that is determined by those 2 points. And then the slope of the secant line determined by the difference of the y values divided by the difference of the x values. And that's interpreted to mean specifically to these 2 points. So f of x plus h minus f of x divided by x plus h minus x, which means just divided by h. So it's the ratio of the change in the y value divided by change in the x value, or if you like, it's the ratio of this length to that one. You know, in the picture, it's this length to that one, but of course, this could be a negative number, that could be a negative number. And so that's the slope of the secant line. And the tangent line is going to be then the limit of all these secant lines as h goes to 0. So basically, as you're keeping this point fixed and dropping this point closer and closer to x, f of x. And the instantaneous velocity is the slope of that tangent line. And the derivative at the point x is defined to be that instantaneous velocity. So how do you write that down? Well, the tangent line is the limit of the secant line. Correspondingly, the derivative of the function at the point, if it exists, will then be the limit of the slopes of those secant lines. So you take the limit as h goes to 0 of the slope of the secant line. And you'll also hear this being called a difference quotient, the limit of the difference quotient as the difference goes to 0. It's another way of phrasing the derivative. And this is notated by just writing f prime of x. It means the derivative of the function f at that point x. It's the instantaneous velocity, if you like. It's the slope of the tangent line to the function at the point x. So before I proceed with some examples, do you have any questions about that definition? See a little bit of glare on the board. Maybe we can. The lights are on a dimmer. I'll try not to mess with them too much. Okay. It's worth doing some actual examples, and certainly we could use this and start computing some derivatives, and maybe we'll return back to that as class progresses. But I do want to start out with a little bit more of a modest goal. So let's look at a like a constant function like y equals 2, and you'll see me use y equals f of x, so like using y and f of x interchangeably. You use y when you're thinking about graphing it because you're thinking of the y-axis, and you use f of x when you want to emphasize that it is a function with x as the input. So here, let's take the derivative at an unspecified, like fixed but arbitrary point x, and let's calculate this from the definition. So we're taking limit as h goes to 0 of. So whenever you have to calculate a derivative by the definition, make sure you've got that definition memorized so you can just write it down every time. And as I'm calculating this, you'll see me try to dutifully just, this is equal to that, and this step is clear from the definition, and this is equal to that, and I'm going to do some simplification. But I'm keep writing down that I'm taking a limit every time, and each of my steps, I hope it will be evident, like what step I'm performing, and that's how you should fill out your homework and exam problems as well. And so f of x plus h, I mean, that's just 2. This function is constant, and f of x, that's just 2. So you're getting now the limit as h goes to 0 of 0 over h. Remember how we calculate these limits? You don't actually have to plug in h equals 0. In fact, you can't plug in h equals 0, but you're asking if h is close to 0, then what is 0 plus h close to? Well, it's close to 0. In fact, it is equal to 0. And we could work this out with the epsilon delta definition of the limit. There's no problem with that, but there's also no quibble here. No one's going to argue with you that the limit of 0, like as h goes to 0, is equal to 0. So that's telling you what? That the slope of a tangent line to a constant function is equal to 0, which makes perfect sense because here's the line, take any point x, and the tangent line is also going to be that same straight line because every secant line is also going to be that same straight line. So this definition, we're going to use it for situations that are more interesting than this, but in this basic situation, it does show us that the derivative is equal to 0. And it doesn't just work for y equals 2, it works for any constant function. So certainly this also proves that if you have f of x equals a constant, like some fixed but arbitrary number c, then f prime of x is nothing but the 0 function. You could even promote this a little bit further. So you could say, like, what about f of x equals ax plus b? So what if you have some linear function? What if you have some linear function I'll draw it as if here's the point B and as if like A is a positive slope. So let's take some point. Let's take some fixed but arbitrary point x and try to calculate what's the derivative of the function at x. And let's use the definition. So let's take limit as h goes to 0 of the slope of those secant lines. And of course this, I bet you can reason it out without actually computing a limit, because if you go to x, f of x, and then you go to x plus h, like up here, and if you draw the secant line between these 2 points, you can see immediately that, well, since you started with a straight line anyway, the secant line is nothing but the function that you started with. So the secant line is still going to be ax plus b, no matter which 2 points you pick. Which is telling me that the tangent line, namely the limit of secant lines, the tangent line is also going to be ax plus b, and therefore the slope of that tangent line is going to be a, and it will turn out that f prime of x is equal to a. But let's see that through direct calculation. So let's just plug in the definition, f of x plus h minus f of x divided by h. And let's see, so I'm taking limit as h goes to 0, f of x plus h. So what is that? That's a times x plus h plus b, and then I'm subtracting ax plus b, right? So just literally plugging in x plus h for x, and then subtracting ax plus b, dividing through by h. So we ought to simplify the numerator. I'm hearing rain outside. It's nice to get rain for once instead of lots and lots of snow. So I'm seeing b cancel. I'm seeing a times x cancel with ax, and what's left over is just a times h. So this is limit as h goes to 0 of a times h over h. And so a times h over h is a constant function that has a hole at h equals 0. But again, when you're just calculating that limit, you're not actually plugging in h equals 0. You're just considering like where do the y values, what value do the y values have to be close to if h is close to 0. So when you're taking a limit, it is appropriate to cancel those h's. Get limit as h goes to 0 of a. It's just equal to a. And I stress, yes, it is possible to work this out with epsilon delta argument as well, but throughout the remainder of the course, we'll be typically arguing without doing that, and we'll be typically obtaining limits that after some algebraic simplification are going to be plain to us what the limit is equal to, because we'll end up with a continuous function after doing some cancellation. Although there are some arguments that are actually kind of intricate and clever that we'll see as well as we get on in the class. But for now, we're really just trying to get used to the definition. So 2 things that we've learned. If you have a constant function, its derivative is 0. More generally, if you have a linear function, its derivative is equal to the slope of that line. Let's go ahead and do this. F of x equals x minus 2 squared. And let's take f prime of 3. So let's go ahead and do this. So, I mean, I've been calculating f prime of x. I could still do that here. I could use fixed but arbitrary letter x. Although, for this particular example, as we're just getting into things, I'm going to choose just to use the number 3 to give you a specific slope of a specific tangent line at the point x equals 3. So let's do this. So let's take the limit. So you're going to see this on homework or test. Given f of x equals formula, compute, using the definition, the derivative of f of x at the point x equals 3. And this is how you'll start that computation. So f prime of 3, by definition, it's equal to the limit as h goes to 0 of f of 3 plus h minus f of 3 over h. So it's just f prime of x, but I've substituted in 3 instead of x. So let's go for it. So let's compute limit as h goes to 0. And I have to plug in 3 plus h for x. So I'm getting 3 plus h minus 2 squared minus f of 3. So that's 3 minus 2 squared. That's 1 squared. That's equal to 1. And now I'm dividing by h. So now you may already be seeing the end game here, like how this is going to work out, because I've got h plus 1 squared, and then the constant term 1 is going to get canceled out here, and you'll see a cancellation with an h. But let's go through those steps. I think I'll use this part of the board to do it. So let's go through those steps. That's the limit as h goes to 0 of h plus 1 squared minus 1 over h. Which is the limit as h goes to 0 of h squared plus 2h plus 1 minus 1 over h. And this is the limit as h goes to 0 of, so this is h squared plus 2h over h. So I'll just factor out an h from the numerator. So I'll say h times h plus 2 divided by h. So, I mean, I combine two short steps into one. 1 minus 1 is 0, and then h squared plus 2h is equal to h times h plus 2, all divided by h. And since we're in the limit, you cancel out those h's. You take limit as h goes to 0 of h plus 2, and the answer is equal to 2. And so this is the principle in calculus, at least for the exercises that we do in this class, that allows you to get away with calculating limits without using epsilon delta definition, because as long as you can do some algebraic manipulation that allows a cancellation and then plugging into a continuous function, then you can just calculate with the limit laws. And many of the examples that we do in this course, yeah, it's just going to be polynomials, rational functions. Trig functions are special. We'll handle those separately. But the domain or the playground of calculus are these formula-based functions that should play nicely with this definition, and you'll have a lot of fun like figuring out these derivatives. Okay, so let's kind of pause for a second. So first of all, any questions about that calculation? Yeah, let me check the chat as well. Yeah, the derivative is the instantaneous velocity at the point. That's correct. So I'll record the work that we've done here. So we calculated the f prime of 3 was equal to 2, which tells us that the instantaneous velocity of this function at the point x equals 3 is equal to 2. Let's do some visualization. Let's do some visualization of this. And let's do it online. I'll show you the Desmos graph. So we looked at f of x equals x minus 2 squared. So there it is. And by the way, so like I don't want to make you think that Desmos can do everything, but for simple functions like this, it can also do some of these calculations. So like if you type in f prime of, what was it, f prime of 3, it'll calculate that for you. So it calculated the limit for you. Desmos can't really calculate limits, but it's got some programming tricks that work for polynomials like this. So this can be helpful for you if you want to, I mean, like if I give you a problem that says calculate the derivative from the definition, and you just like write down 2 with no work, of course we can accept that. But I think that Desmos is really good to like check your answer, you know? So like you could do some work and then just type it in here and check that the answer is correct or incorrect, and that can and should facilitate your homework. Okay, but fine. So when x is equal to 3, the slope of the tangent line is equal to 2. So let's try to draw that tangent line. So when x is equal to 3, what's the y value? Like it's going to be f of 3. And for us actually having to draw it, f of 3 is what? It's equal to 1. In retrospect, makes sense because 3 minus 2 is 1, like 1 squared. So it's the point is up here at 3, 1. You can see it in green. So if I calculate the slope of the tangent line and calculate it to be able to be equal to 2, I can now take this slope and this point and very quickly write down a formula for the tangent line. In fact, you could use this point slope formula, which is like y minus, y1 equals slope times x minus x1. Remember that formula? But here our x1, y1 is x f of x, and our slope is f prime of 3. So let's do that using this notation. So let's take like y minus 1, and that's going to be equal to f prime of 3 times x minus 3. So I just used the point and the slope to immediately give me the tangent line. So this confirms for you the instantaneous velocity really is equal to 2, and that really is the tangent line. I wonder if we could put like a slider in here, like what if I did y minus f of c equals f prime of c x minus c, and add in a slider so that I can show you different tangent lines for different values of c. So if c is equal to 1, so look there, you get that nice tangent line. If c, yeah, you can see the tangent line. Like, you might not think this is cool or anything, but I think it's really cool. You can see the tangent line sliding around because what I'm doing is at each point c, we're calculating the slope and just plugging it into that point slope formula. So back when c is equal to 3, you see it lining up with what we had before. And as c increases, the slope of that tangent line has to increase to keep up with it. I have too much fun with this. Okay, I'll stop. But any questions or comments on that? So things you definitely could be asked, given a function, calculate the derivative at a point, and also given a function, graph me that tangent line at the point, and you're going to need to know how to do that. And what we've seen is that there's this nice formula for the tangent line at the point, x, f of x, and with slope given by f prime of x, you just plug into this point slope form, and you'll get that your tangent line has to be y minus f of x equals f prime of x times x minus, well, I guess this isn't going to work out because I can't use x for the variable and also x for the point that I'm taking the derivative. So let's use a. Say you fixed x equals a and then f of a. And then I want to make, so the tangent line is going to have slope f prime of a. Do you see how I couldn't use the variable x here and also the same variable for the tangent line? Two different functions, tangent line versus function. So I'll just say the formula for tangent line at x equals a should be y minus f of a, just using point slope formula, equals the slope, which is f prime of a, it's that limit, times x minus a. So this is the formula for the tangent line to the function f of x at the point x equals a. And so that's something that you will need to be able to calculate. So one other thing, there's another definition, another equivalent definition of derivative that you will sometimes see, which goes as follows. So suppose that you've done this. So suppose you've said, well, let's take x equals a and let's take f prime of a. And then if I look at the slope of the secant line, that's going to be, let's look at the slope of the secant line, say, draw a picture. Try to use the same example that I had before. But this time we're picking x equals a, right? And another way you could model this or conceive of this is instead of going from x to x plus h, you could go from a to some other variable, which, I don't know, you might as well just call x. So here you've got a, f of a, and here you've got x, f of x. And you draw the secant line between these 2 points, and you see the slope is going to be f of x minus f of a over x minus a. Just because you've used some different notation, but it's the same thing. And therefore, when you take the limit of the slopes, as this point approaches that one, instead of h going to 0, you're going to have x approaching a. So you'll want instead the limit as x approaches a of the slopes of the secant line, f of x minus f of a over x minus a. And this is f prime of a. So this is just an equivalent definition of the derivative, just using different notation. But it all means the same thing. And I can show you how to convert this into h's, right? If you want to think of a and then going out by h, then you can just write x is like a plus h. And if you make that substitution, well, x going to a is the same thing as h going to 0, isn't it? So you can write this as, well, if x is going to a, just changing the variable to h instead of x. A is fixed. X goes to a is like saying h is going to 0. And then f of x, well, x is just equal to a plus h. Keep a like it is. And then again, x is a plus h. So a plus h minus a is just h. So just like a little word of caution, it's depending on which notational setup you use, whether you like to say a and then a plus h and take the limit as h goes to 0, or whether you like to say x and a and take the limit as x goes to a, really doesn't matter. Modern mathematicians will prefer this definition to the other one because we think it's easier to work with in theory and in practice a quantity going to 0 instead of a quantity going to another quantity. But again, it doesn't matter, and you will see both in this course. But just to be aware that they're equivalent to each other. They express the same thing. That's the important part. Okay, so we've seen two different definitions for the derivative. We've done a few calculations. We've shown that the derivative of a linear function is equal to the slope of that line. We've played around with Desmos. I instructed you on how to make a slider to get lots and lots of different tangent lines for a particular function. And I think that's pretty good. I mean, like on a normal day, we might sort of pick some chapter exercises to go through at random, further enforce our understanding. But since we've got a test on Wednesday, I want to at least pause and allow you to ask me any questions that you have about the test, or like anything that's not, maybe I didn't explain so clearly, you'd like me to re-explain. Anything at all, the floor is yours. So not hearing any questions, and you can also come to office hours today. Not hearing any questions, let's take the remaining time to do just one problem at random from the chapter exercises. And certainly doing this stuff will also, I should think, help solidify your understanding of limits and so on. So I don't think this material is wasted when it comes to studying for the test. So yeah, this is number 29 from section 3.1, if you want to follow along, but I'll also write it down. presently. It's just going to be one of those problems that says compute the derivative and then write down the equation for the tangent line. It's one of these bread and butter problems. So let's take f of x equals two x squared plus 10x. Let's take a equals 3. Compute f prime of a, and also find the formula for the tangent line at x equals a. And I mean, a is equal to 3, so I may as well just say compute f prime of 3 and find a formula for the tangent line at x equals 3. So take 5 minutes. Please do that problem, and then we'll discuss. Okay, after giving you some time to work, I'll try to do it also, and you can compare to what I end up with, and let me know if I'm making any mistakes. Naturally, we should compute f prime of 3 first. And then just plug it into the formula to get the tangent line. So f prime of 3, I've got to go back to the definition. I can use any definition that I want, but I'm going to use the h goes to 0 definition. And so I'm going to be writing down limit as h goes to 0, f of x plus h minus f of x. So I'll just go ahead and make that substitution. X plus h squared plus 10 x plus h. That's my f of x plus h. And I'm subtracting f of x, which is 2x squared plus 10x. So it's important to keep track of your minus signs so as not to get stuck anywhere. So that's what we've got. Not so bad. Yeah, definitely I need to expand this out. So this x plus h squared, so that's 2 times x squared plus 2 xh plus h squared. And then plus 10x plus 10h minus 2x squared minus 10x, everything over h. So now you're hoping that terms that don't involve h will cancel themselves out in the numerator, and you'll be able to factor an h out of something that's left. Looks like we're on the way to seeing that happen. Here I've got 2x squared canceling with 2x squared. Here I've got 10x canceling with 10x. And what's left? 4 times x times h plus 2h squared plus 10 times h. Everything that's left has an h as a factor. Go ahead and make that factorization. So what's left? It's h times 4x, 2 times 2 times x times h, plus 2h plus 10. Everything divided by h. Did I miss anything? I don't think so. Got the 4x, 2h, and the 10. And dividing through those h's, and then take the limit as h goes to 0, which I can get now through direct substitution. Leaving me 4x plus 10. And where did I kind of messed up a little bit, because I started out with 3 and ended up with x. And so what I ended up doing was I did something more general without thinking of it. I just went ahead and calculated f prime of x. And so I did something more general. You can take this calculation and now just plug in 3. So 4 times 3 is 12, plus 10 is 22. So yeah, that's just a little a mental slip there. Plugging in 3, you would have 3 plus h, 3 plus h, and then 2 times 3 squared, 10 times 3, and that'll actually simplify your work a little bit. It'll make it a little bit easier because you don't have so many terms. I did something more general. I calculated the f prime of x for any x was 4x plus 10, and therefore, in particular, plugging in x equals 3 would give me 22. So f prime of 3 is 22. And now what's the tangent line at x equals 3? So when x equals 3, what's f of 3? So that's just going to be plugging in the number 3. That's 2 times 9, that's 18, plus 30, so I think we get 48. So you want the line that has slope 20 through 22 and goes through the point 348. So I'll simply take y minus 48 is equal to 22 times x minus 3. And so that's my tangent line. So if I'm doing homework to submit to my calculus teacher, what I might do is go on Desmos and actually graph this function and graph the tangent line and just verify that it actually is tangent, that everything's good. Of course, you don't have to do that, but that's just one way to check your work. If you like. And I mean, since we've got 2 more minutes left, maybe I'll go ahead and check it. But any questions for me, you can put in chat or yell them out. But yeah, let's go ahead and put the instructor on the spot. Let's see whether or not I calculated this correctly or whether or not I made a mistake. So the original equation was f of x equals 2x squared plus 10. So that's this x squared, 2x squared plus 10x, excuse me. So that's that parabola, and we were asked what's f prime of 3, and that's 22, so that's just like we calculated. And so let's also look at y, well, f of 3, I guess, is 48, just like we calculated, and so then y minus 48 equals 22 times x minus 3, and yeah, it looks like we are going to be tangent at x equals 3. So x equals 3, like you're up here at 48. So here's the point of tangency. You can see the green and the red line are like really close at that point. Pause for any question. I got a question about the exam, not about the question. So the exam on Wednesday also has 6 questions, and will cost 1 class to finish it. So the exam will be written so that you can do it in 1 class period. So you'll have 55 minutes to complete the exam. I haven't written it yet, so I can't promise how many questions it'll be, but it'll be designed to be completed in 1 class period. Yeah, so looks like we calculated this problem correctly and checked our work on Desmos. So that's it for today. Learning objective was 2 definitions of derivative. What is the tangent line, like how to graph that from calculating the derivative, doing some examples, making sure we're prepared for the test. So have a great day, everybody. I'll see you again on Wednesday, and we'll do the test at that time.